that time until now, I've just been teaching all the way. So I have no idea what's going on for them. Have you figured it out? You figured it out already? Awesome. Like, can you tell me? Because I was in a fluster just now. I couldn't get my head around it. Wow, today's traffic is bad, man. I keep hearing all these people honking all over the place. Sorry, what's the rationale between where's the distance at? They said 3/4. Why is that? Oh, is it because it's 1.1504? Eh, no. What am I doing again? I get very confused again. No, sorry. I can't wrap my head around it. Let me turn on the aircon now. Can hardly breathe. Huh? What? Oh. Oh, what? The phase difference. The phase difference. I just realized it's a phase difference. It's not to do with the intensity because, for the longest time just now, I was like trying to figure out what the heck. Why is it that you know, the like, is it based on intensity? But I don't know what's the intensity meeting at the point, right? Then now that I second look at it, right, then I realize, oh shoots, I'm supposed to use this phase difference here. Like, yeah. So how many squares is that? How many squares is it off by? 3 squares, right? Yeah, I mean, oh wait, is it 3 squares? Is it 3 grid squares? Do I see 3 grid squares? I see 3, right? It's 3 grid squares, right? What's one full wave? How many squares is one full wave? One full wave is how far? How much? You have to go and look for some nice numbers. I think I see one here. No, hang on. So I'm looking at one of the waves now. How many grid squares is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 and a half. So basically it's 3 over 12 and a half. Or it could be taken as 12 and a half minus 3, then divide by 12 and a half. No, but the phase difference is only 3 grid squares. 3 divided by 12 and a half. That's 0.24 away. That's close to 0.25 lah. Okay, so right in the middle is when the two waves perfectly overlap, right? And point P, and then this is the next. Oh, that means I think it's because of the way we draw it. Okay. And that's the next. I mean, whatever it is, that's the next time, right? That they completely overlap. So at this point is when they are out of phase. That means when they are not overlapping each other. So I guess the question is, how far does it have to move by in order to be completely out of phase? Like, how much more does it have to move by to be completely out of phase? Another 3 grid squares, right? So basically, this thing. You see point P is what? 3 over 2 pi. Yeah, 1/4. Yes, it should be 1/4, not 3/4 though. Right? Yes, that's right. It's closer to S1. So it's on the left side actually. So point P will be on the left side because it's closer to S1 than it is to S2, and it is 1/4 of X away from the center. On the right side, I mean, depends on where you're looking at it from lah. If you look at the back of the screen or if you look at the front of the screen, then I guess it's different, right? But I'm saying that I'm saying that it's on the left side because it should be closer to S1. That's why the amplitude is higher, right? So if it's like trying to figure out where the position of it, I would say that position of S would be like somewhere here because it's closer to S1 than it is to S2. But it's saying that it's on the right side. That's, I mean, it really. But again, like I said, it depends on how you're looking at the screen. If you look at the screen from this direction, then P is on this side. If you look at it from the back, right, then P is on the right side. So it doesn't matter, actually. Yeah. But it's 1/4 of X, right? Three quarters. Oh, okay. That means it's on. That means instead of here, it's on this side here like that. Yeah. Okay, it's basically on this side here like this. Okay, let me just tell you this, guy. In the grand scheme of things, right? This kind of question is waste time one. You understand? Like if you feel like you absolutely must get 100% of all the marks, right? This is we can work it out after the paper. We can figure out, oh yeah, that's actually what I mean. But during the paper itself, I think very rarely anyone will be able to fully grasp that. Oh, it's actually P is like on this side here like this, like 3/4 of the way, right? I mean, I just calculated it, right? 3 grid squares for 12.5 is 1/4 of the way, right? So down here they're arguing that because it's the S1 is leading S2, that kind of thing, so therefore it's closer to S1 and all that. All these things are just kind of like in the. Would you be thinking about that when you are doing this paper? I don't think so. So for this 1 mark, right, it's not a good use of time. In fact, it's also not a good use of time trying to figure this out like any further than this. Can? All right. I think we've got like more marks to get. Do you want me to do this? This one okay? The next paper, right? The other scans, right? Okay. Is it this one? This one? Okay. The next question, okay, which is this one here, is it? Oh, this one, no issues? This one? Sketch the displacement time graph for the first 4.5 seconds of the sphere's motion in the liquid. Right? Okay. It says it reaches terminal velocity at 2.5 seconds. Sorry, what? Question 2. Next page. This one here. This one? Okay. Sorry, what's the actual question here? Like, sorry, what's the actual question that you have here? Part 5. Part I. Oh, what's the radius of the circular motion of the ring? Oh, hang on. There's a string here, is it? Oh, there's a string there. Is the string horizontal? Okay. So there's a string here. and the string is horizontal. So there's a ring that's there, and then the string is looped around it, right? Like this. Okay, okay, okay. So the length is 8L, right? Okay. You're not gonna like this, but it's basically just math. So let's say we call this the hypotenuse, and we call this the adjacent, or maybe it's R. Let's call it R. Okay. All right, let's call this R. Basically, H plus R equals to 8L. And then H squared equals to H squared, sorry, 4L squared plus R squared equals to H squared. Yeah, the length, right? The entire length, they say that the smooth ring is threaded through. So I guess in a way, poor diagram. Not how to see, right? So 4L squared plus R squared equals to H squared, sorry, equals to H squared. Yeah. And then you kind of have to do some simultaneous around here. Good luck. Yeah. I'm quite sure you know how to do this. Okay. To be honest, these seem very, very old type of questions. So where are you getting these from? 2022. 2021. Okay. So I think in recent years, not this kind of annoying questions anymore. Yeah, which part of this is physics? Then you spend time doing all these things here. It's not very physics type of question anymore. Okay, what's the next one? That's it for this paper. Then we have another scan, right? We have one more scan. Is it? You double check with me, come. So will the stone be able to escape, right? Mm. Mm. It's not equal to the orbital speed, okay. Yeah, that's right. Wait, hang on. What's your answer for this? Will it orbit or not? It won't orbit, right? And the reason is greater than the escape speed. You say escape speed. Okay, that's fine also actually. Okay, so you know what? Maybe I'll touch on this a bit. Because this orbital thing is usually a problem. Is someone going to pick you up though? That's the next question. No, so you're going to go home by yourself. Okay, can. And does it take long for you to go home? Where do you stay? Okay, so it's not so bad, right? Downtown line can reach, huh? Okay, no, because in case you are hungry, you want to go home, you are dinner, or you're tired or something like that, right? Okay, right. Wait, So I start off first with escape speed, right? Let's say planet Earth, right? Planet Earth, okay? And then I have a rocket, okay? And I want it to escape. When we say these kind of things, right? Escape to where? We want it to escape to infinity. So what kind of energy must we give this rocket in order for it to escape to infinity? What type of energy do we need to give it? We need to give it KE. What is it going to exchange its KE for? Right? So if you want this thing to escape to infinity, you want him to escape to infinity, then you give him KE, escape KE, right? And his final KE here will be 0, right? Because all the KE will be converted into GPE. So escape KE is defined as the minimum energy required by the object to launch off from the surface to escape to infinity, right? But the keyword is minimum. So what happens, so what's the equation look like? The equation will look like this. So half mv escape squared is equals to gmm over r. My usual notation, I like to use big R for the radius of the planet, small r for distance, any distance, right? Usually small r will be bigger than big R, right? Because this will be the radius of the planet. You understand this? Okay, so there you go. What happens if you, so you can calculate the escape speed, right? Do you understand that the small m cancels off? What does that mean? Correct. So that means that any rocket, right, that you have, bigger rocket, smaller rocket, molecule, right, for a given planet, all of them have the same escape speed. They will have different escape KE, they will need different escape KE, but they will all have the same escape speed. Correct or not? Okay? Okay, good. So that's the thing, right? You're trying to escape to infinity, right? And it's based on the mass and the radius of the planet. If the mass is big, then it's very hard to escape. If the radius is big, right, then it's a little bit easier to escape. What happens if you give this rocket more than the KE? More than escape KE, what will happen to it? It will fly to infinity, but then it will have leftover KE. So the idea of escape KE is the minimum energy you need to send it off to infinity, but then when it reaches infinity, the KE is 0. That means it will stop moving, it will not drift, it will just stay where it is. Okay? But if you give this rocket more than the escape KE calculated by the planet, then this rocket will fly to infinity and then continue drifting off at a constant speed. Like its remaining KE will be left and nothing else will be removed. No other KE will be lost. It will continue drifting off into infinity and beyond. Right? With a constant KE. Do you understand that when the rocket is launching off into infinity, it moves off with a decreasing deceleration? I'm just trying to cram in a lot of things, so, you know. Okay? So the rocket will decelerate as it flies off, right? It decelerates because the gravitational pull is strong. But as it continues to fly further and further away, what happens with gravitational pull? It gets less and less, right? So the rocket will fly off with deceleration that's getting less and less because the effects of gravity is getting weaker and weaker. So decreasing deceleration. It doesn't accelerate lah. Right? It decelerates, right? Because we know that it reaches to infinity with a slower speed, right? Yeah, because it's exchanging its KE for GPE, right? What's the maximum amount of GPE that you can gain? Like, what's the maximum amount of GPE that you can have? 0. 0 GPE is maximum GPE. Do you understand that all objects on the surface of the planet has the most negative GPE? You get that right? Okay. So you understand the concept of trying to escape to infinity so far? Okay, none of the things I said sounds foreign, right? Okay. So what happens if, let's say, you give another rocket, you give it 0.8 escape KE? What happened to this rocket? Huh? Yeah, it won't escape. In fact, what would it do? Exactly. So if you don't give it enough KE, it will launch out into space like this, and then, right, it'll crash back to Earth. You understand this? Like the amount of KE will be able to help it get it to that point there. I'm pretty sure you know that in order to calculate how high it can go, this H, right? To calculate the height that it can go above the Earth's surface, right? I'm hoping you understand that it's actually the difference in the GPE. So it's GMM, right? Negative GMM over R plus H minus negative GMM over R. Are you aware of that? Okay, then you can find H. This will be a smaller negative number, When you minus minus, this will be a bigger positive number. So you end up with a positive value of h. Right? That's the height above the surface. Be very careful whenever you're doing gravitational questions. At least I know that teachers love to trick students by giving you height above the surface, which means you need to add it to the radius of the planet, because all the gravitational stuff that you do must always be referenced to the center of the planet. Are we okay so far? This is escape, huh? Okay. Any particle that wants to escape to infinity will have the same escape speed. So my next question to you is, how about orbiting then? How about orbit? Let's say you want to orbit a satellite. Okay, so let's say we draw a satellite here. I want this satellite to orbit around Earth. Right? Do I give it the escape KE? No. If I give it the escape KE, this guy will fly away to infinity. I don't want that. Right? So I give it a certain launch KE, but that's going to be a fraction of the escape KE, like maybe 0.2 escape KE. Like, no, not enough. So it will launch up to this point. Launch out at this point. Okay? But I want it to orbit. So what must happen next? Because if nothing happens, you'll crash back down to Earth. So what must happen next? It must turn 90 degrees. So it needs to turn 90 degrees like this. And then it needs to boost again. Because right now it's just turning without any speed, right? So it needs to boost again. It needs to gain some sort of velocity. R omega. Right? That's R omega. Okay. Right. Well, it actually depends. Right? It depends on what speed you want, right? Okay. So the idea here is this rocket must turn 90 degrees and give off its own orbital speed like this, right? It needs to launch off orbit, right? Like this, huh? Then you'll be able to cover one full circle, right? And then it'll continue orbiting. Is there any equation that can help us find a V orbit? Very good. So GMM over R squared, right? Notice how I use R. That means I'm using small r here, which also means that I'm just using this r here from the center to the orbital height, like this. Okay, this is r. Okay, and by doing so, GMM over R squared is equals to mv orbit squared over R, right? Is there an expression for V orbit? Well, it doesn't matter about the mass of the satellite, right? So what do you get? Square root of GM over R. Okay, GM over R. So if you want to find out what's the orbital speed required to orbit at this distance R, the generic equation is just square root of GM over R. Okay? I wouldn't use R omega because omega means you need to know the period, right? 2 pi over t, but I don't know what the period is, right? I will just use whatever I have here, right? So this is my V orbit here. Okay, Can? Not done yet. Okay. So now the thing is this, right? What happens if this satellite is now orbiting, right? What happens if it encounters some debris here? Let's say there's some obstruction here, right? And the rocket, right, encounters this debris field. What happens to the rocket? I erase some stuff, huh? Let me erase some things here and here. Let me just erase some of these things here. What? I mean, it's drag lah, basically it's drag. But what happens to the rocket? I mean, it will lose energy, right? So what will happen to it? Yeah, good. So a common misconception that students have is they think that, oh, the rocket encounters this and then it will drift off into space. That's absolutely wrong. Because if you lose energy in a gravitational field, you will fall inwards towards the planet. In fact, in order to drift off into space, you actually need more energy than now. You need to basically give it some boost and then so they can fly across. Right? Otherwise cannot. Otherwise it encounters this thing. The first thing that will happen is that it will start to fall. Okay? So when we talk about orbital energies, you need to recall these graphs. Right, these ER graphs, you need to recall these three graphs here, like this. Right. Do you know what these three graphs are? What's the top graph for? Middle? Bottom? So KE, TE, and GPE. So your job is to understand that the moment the rocket encounters this debris field and loses energy, it loses total energy. So its total energy will drop from a high value and it will drop to an even more negative value. So his total energy is impacted already. You understand that? So this rocket would then, right, drop to a lower orbit. It will continue to orbit at a lower orbit. Right? It will continue to orbit at a lower orbit like this, but it's stuck at the new lower orbit. Why? Because his total energy is now less. But the ironic thing is, even though it's now at a lower orbit, even though it has lost energy, what happens to the KE of the rocket? Yeah, it actually goes faster. So the rocket is actually orbiting faster. That's like the string thing, right? That's wrapping around a stick. Right? So it's like if you have something like this, right? It's orbiting around like that. It's orbiting, right? Like this, right? It's using a string to orbit around the thing here. But what happens if you let the string wrap around it? Like this. So as it's being wrapped around, it becomes faster and faster. So that's what's happening there. Okay? But it's not fast enough to go back up into a higher orbit. In order for it to go back up into a higher orbit, you need to increase the total energy. Are we okay in this? Can I? Okay, good. So there is another famous equation. There's another popular question they like to ask. Is this, right? Assuming none of this happens, none of these bad things happen, right? It didn't fall to a lower orbit. Let's talk about the satellite, right? Doing its normal thing again, right? The satellite is this thing is a bit big, so let me just reduce the size of it. Okay, something like that. All right. Let's understand one thing. After it's done its orbit for a couple of rounds already, I want to send this rocket all the way out into outer space. Right? So I want this rocket to go to infinity. Right? So this is escape from escaping from an orbit. How do I find out how much energy it needs? Right? Find energy required for satellite to go infinity. So how do I find out how much energy do I need? Good. Right? So basically you're looking for total energy. So all you have to do is just figure out, okay, it being here, right now, what's the total energy of this satellite? Good. Negative half GMM over R, where R is from here to there. Right? It's the whole R here, like this, right? Okay? So negative half GMM over R. So you make this total energy 0. That means you give it this amount of energy, this rocket will fly to infinity. Correct or not? Okay. Now, with regards to that rock question then, right, back to the rock question. So the rock question is basically asking you, right, when the asteroid, right, when asteroid like approaches this part, it's like a tangent to this thing here, right? Your job is to find out whether or not it will orbit, right? So you have to find out, firstly, for it to orbit, does it match the orbital speed at this height? Right. So one of the ways you can go and calculate, okay, what's the typical, right, orbital speed at this for this orbit here, like this. Right. So what's the V? What's the orbital speed here, like that? Yeah, square root of GM over R. Right, GM over R. Right. GM over R. And then you compare the speed. If this speed is more than this, then no. Right? It will fly, it will not be in this orbit. But could it orbit at a higher height? Could it go into a bigger orbit eventually, you know? Like you know, I don't know, maybe like hit a greater orbit and all that. Then you have to check what's the escape velocity at this height. So there is a thing whereby, you know, you can ask this question where, right, at this height, right, at this height here, right, if you're trying to escape from this height, what is the escape speed there? Okay, but before you answer this question, let's understand again from the previous page. Sorry, I forgot to do this. From the previous page, right? Escape speed is what's the equation for escape speed? Square root of 2gm over r, and this is if you're escaping from the surface. Notice how the difference is just basically square root 2 lah. Right, compared to orbit. So for the escape speed here, if you're at this distance, right? Let's not call that h. Let's call this r plus h. So then the v escape will be square root of 2gm over r plus h. Then you can check if this speed is more than this, then it will escape to infinity. If it's less than this, but more than this, then it may orbit around Earth, right? It may orbit around Earth, okay? But very, very far orbital distance. Is that what the question is asking for? I don't know. I haven't read the question yet. I mean, you've read the question, but I'm just trying to run through the entire, like, you know, possible scenario. Oh, why it won't orbit lah, right? Yeah, why would it won't orbit at y lah? Then your answer is just simply is more than the orbital speed lor. Yeah, therefore it will not orbit at y. Yeah. As to what happens to it later on, nobody knows. Yeah. Nah, finding the orbital speed and then all that. Can ah? Okay. Anything else here? This hyperloop thing. You figured it out. Okay. So as seen by the outside is parabolic. As seen by the draw the position when it hits the floor. Oh, it will fall directly down. Like it will hit the ground here. It won't hit in front. As in you'll hit right in front of him here. Like your box must be directly below. Yeah. You know why, right? Because the object has forward motion with you. Okay, I give you one more. I give you one more scenario to think of. Hot air balloon. Right? Hot air balloon rising at 5 meters per second. You drop a sandbag. What's the path of the sandbag? Yeah, it goes up and it goes down, right? Like this. Okay, can. So the initial speed of the sandbag is 5 meters per second. But it will start to decrease, whereas the hot air balloon is still maintained at 5 meters per second going upwards. Okay, so this one you understand. Okay, all right. I don't know what you don't know. Is there anything else you need to clarify? Did you clarify the superposition stuff? You understand? Oh, yeah, oh, you caught up on the revision. I don't know whether you caught up on the revision. You did. Okay, so you watched all the different formulas and different single slit, double slit, and the equations and all that. Okay, right. So just be aware that the for single slit, double slit, and all that, I think the modulation one, honestly speaking, shouldn't they, like, most schools shouldn't ask modulation anymore, to be honest, because modulation only came out one time in the A levels, and because of that, all the schools all went haywire, and then like, oh, we started to central max to the first minimum. So it's the angle from central max to first minimum. Okay? But what happens if it's double slit? Double slit the pattern like this, right? So your pattern looks like this. Is there an angle? What's the equation for single slit? Theta equals to lambda over b. Theta equals to x over d. Right? This x is what? From central max and first minimum, right? So that's x. But then the other so what's the equation for this double slit? X equals to n lambda d over a, right? So a is the slit separation, d is the distance to the screen, right? Lambda is the wavelength, but x is what? What is x? Yeah, so x is fringe separation, right? Did your teachers ever, or did you ever do this before, whereby you can rearrange this equation, x over d equals to lambda over a? Do you see that before? So we don't, for single slit, double slit, we just small angle approximation. So you don't have to do tangent theta and sine theta for small angle approximation. And then we just put this as theta. Right? This is theta double slit, but this angle is from where to where? The angle is from one bright fringe to the other bright fringe. Okay? Whereas for single slit, the angle, right, this theta, right, the theta that you see here, theta single slit, right, theta single slit is from central fringe to the first minimum. So sometimes some teachers, right, they try to be annoying, right? They give you the distance. They tell you that, oh, I have a distance from one maxima to one minima. They tell you that, oh, it's 5 mm. That means that x is 10 mm, right? So just be very careful. So sometimes they try to play tricks on you. Whereas for this one here, if they tell you that, oh, between the central bright fringe and the first minimum is like 5 cm or something like that, right? Then that's okay, right? We just take it as 5 cm. That's fine, right? Because that's the difference between single slit and double slit. Then you have your diffraction grating, right? Your diffraction grating. What's your diffraction grating all about? Diffraction grating like that, right? Then you have your laser, right? Then you get dots, right? Then the diffraction grating equation is d sine theta equals to n lambda, and tangent theta equals to x over d. But for diffraction grating, the theta and the x is from where to where? Central max, which is n equals to 0, right? If you are looking at the first maxima, then that's theta 1. But if let's say I want to look at the second order, the angle is from central max to second order. So for diffraction grating, is from center to the nth maxima that you're looking at. Single slit, center to first minima, nothing else. Double slit, bright fringe to bright fringe, any bright fringe, dark fringe to dark fringe, any dark fringe, any adjacent dark fringe, any adjacent bright fringes. But when it comes to diffraction grating, central max to the nth order fringe. That's the theta and that's the x. Right? So this one is like x1. Okay, anything else? If nothing else, then I am done.